All right, now that we've explored how we might be able to match the first few derivatives of a function with the derivatives of a polynomial, we're ready to define the Taylor polynomial in general. So the Taylor polynomial of order n for a function is just plugging in the values that we just found for the coefficients into a sum form. And so we're still going to have the kth derivative of f evaluated at c divided by k factorial, and then we're going to have an x minus c to the k. The reason why these are k's instead of n's is because this n here already means something different. And so the order of a polynomial just corresponds to the maximum power that you plug in for x minus c. And then a Taylor series is the word for if we talk about the infinite polynomial. And so if we just replace the n with an infinity, then we're talking about the Taylor series for a function. And so here I'm being really careful to use this twiddle symbol instead of an equality, because at this point we don't know whether or not a function can actually be represented as its Taylor series, and that's a problem we'll talk about in the coming days. One more thing in terms of terminology, when c is equal to 0, and so in other words, when we're talking about centering a Taylor series at x equals 0, then we sometimes say that the series is a Maclaurin series instead, or a Maclaurin polynomial. So Maclaurin series, same thing as Taylor series centered at 0. Okay, let's look at finding the Taylor series for e to the x centered at x equals 0. And then we'll try and use that information to find the Taylor polynomial of order 3 for e to the x. And so in order to do this, I'm going to need to find the pattern for what happens for the derivatives of e to the x. And so I'm going to do this by writing out a table. And so in my table, I'm going to have lines devoted to f of x, f prime of x, f double prime of x, f triple prime of x, f quadruple prime of x, and so on. And so the reason why I want to figure these out is because I'm going to need to plug them in order to find the Taylor polynomial. And so in this middle column, I'm just going to simplify what the derivatives would be in terms of the function. And so if I take one derivative of e to the x, I still get e to the x. If I take two derivatives, I still get e to the x. If I take three derivatives, I still get e to the x, and so on forever. And so this table was pretty boring, but I want to structure things this way because in the future it'll be helpful to have tables like this. And then in the final column, I'm going to plug in x equals 0. Typically, I'd plug in whatever the c value was. And in this case, c is just 0. And so when I plug in 0, I get a 1 over and over and over again for all of these derivatives. And so that's just telling me that the nth derivative evaluated at c is always just 0 in this equation. And so if I plug in to this equation, the sum of fn of 0 over n factorial times x minus c to the n from n equals 0 to infinity. In this case, the c here is just going to be 0, and the nth derivative at 0 is always equal to 1. And so that's 1 over n factorial times x to the n. And so at this point, this is the Taylor series for e to the x, 1 over n factorial times x to the n. And so now if we want to find the third order Taylor polynomial, then I just write out terms in this series until I have a term of degree 3. And so when I plug in n equals 0 into this series, then I get x to the 0 over 0 factorial. That's just 1. When I plug in 1, I get x over 1 factorial. That's just x. When I plug in 2, I get x squared over 2 factorial. And when I plug in 3, I get x to the third over 3 factorial. So in this case, t3 of x, or in other words, the degree 3 polynomial that agrees with the first, second, and third derivatives of e to the x, that's just equal to this.